So a sequence is an ordered list of numbers, right? That's all it is. It's a list of numbers. And each term in the sequence, each number in the sequence is called a term. So, for example, this here, right? 1, 3, 5, 7, 9. Do you see how it's just like a few numbers separated by commas? It's just a list of numbers. Now, in this list, there are 5 terms. And that's why it's called a finite sequence, because it contains a finite number of terms, right? You could have a finite sequence with, 75,000 terms. That's still a finite sequence because you know exactly how many is in there. As opposed to, you can have an infinite sequence, which contains an infinite number of terms, like, for example, this one, 2, 4, 6, 8, ... and that goes on forever. And it's all the even numbers in the universe, and it never ends. That's an infinite sequence. Now, terms in a sequence are labeled A1, A2, A3, A4 with subscripts. Okay, just like in a matrix, right? You had like A11, A12, right? These are like their names. Or instead of starting at A1, you might start it at A0, right? Like this. My preferred way is starting with 1. It's like easier to, figure. Okay, a generic term is given the label A sub n, right? So like A sub n, so suppose you take a sample term A sub n, blah, blah, blah. All right. Now, how do we call terms that come before or after something? So, for example, if you have a list or a sequence, and it's 1, 3, 5, 7, 9, 11, 13, 15, 17, right? Okay, so this is A sub 5, right? That's the 5th one. Okay? What's the name of the one that comes right before it? A sub 4, because you do 5 minus 1. What's the one that's 2 places before it? A sub 3, because you do 5 minus 2. Do you see that? So what's the term that comes right after? It's A sub 6, because you do 5 plus 1. What's the one that comes 2 after the 5? A sub 7, because you do plus 2. Similarly, if this was A sub n, then the one right after it would be A sub n plus 1, or A sub n plus 2. Okay? Or the one before it would be A sub n minus 1, and then n minus 2. Okay? So going back here, terms that come before or after will be labeled as A n minus 1 or A n plus 1. So for example, a list, right? This is A sub n. The ones before it are A n minus 1, A n minus 2, and then after it, it's like this. Okay, so much about labeling. Okay. A sequence, right, can be represented as a function. Now, an explicit formula gives you a recipe to generate all of the terms in the sequence. So for example, you have this mystery sequence. You want to find the first term, the second term, the third term, the fourth term. This function gives you a recipe to do that. So take a look at what this is. It says to find A sub 4 if A sub n is, 3n plus 2. All right? So whatever n is, in this case, n is 4, you plug it into that formula and you get that number. So for example, A sub 4 would be 3 times 4 plus 1 over 2, 13 over 2. Any questions? And with that, you can generate the whole list until you're blue in the face. You can find the first term, the second term, the third term, the fourth term, the millionth term even. Okay? Yeah.
Is that the
No, that specific list, that specific sequence. So each sequence has its own formula. All right? Okay. All right, so let's move on. Here, we want to find the next 4 terms in the following sequences. So for this, we're going to go back to, like, remember what you did in geometry or algebra 1, like basically find the patterns. So what you want, and you know what, some people are so quick with these, like it's like magic. Like they'll look at a sequence and I'm like, oh, it's like blah, 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 blah. Okay, I'm not one of those people. I always have to like figure it out. So here's what I do. How do you go from the first number to the second number? You can subtract 4. Now let's see if that works for this one. Yep. And this one? Yep. Okay, so if it works like 3 consecutive times, then you can be sure like it's pretty legit, okay? So the next few are negative 13. What else? Yeah, negative 21 and 25. Negative 25. Okay, what about this one? Plus 3. Oh, plus 5. Oh, then it's plus 7. Look at that pattern. So you're just adding the next odd number, right? So then it will be plus 9. It's 26. What's the next one? Yep, and then comma 50 and 65. Okay, awesome. Okay, here we're not given a pattern, we're given the formula. We want to find, okay, if it's the next 4, well, we have to start from the beginning here. So we're going to do a sub 1 is 1 cubed plus 1 is 2. A sub 2 is how much? 9. A sub 3? 28. 65. Okay? Questions? So far, so good? Yeah? Okay. All right. Sometimes you have what we call a recursively defined sequence. A recursively defined sequence is different from these, right? In that you have a few initial values. Then each term is defined using the first few terms. So for example, here, when we had to find A1, A2, A3, A4, they were each independent of each other. But for recursively defined functions, in order to find the 4th term, you have to use the 3rd term. In order to find the 5th term, you have to use the 4th term, right? That's like, it's recursive, right? Like going back, back, back. An example of a formula is this. You will be given like the first term or the first few terms. That's your starting point because you got to start from somewhere. And then, so a sub 1 is 1. And then a sub n, you know, like all the terms that come after, is a sub n minus 1 plus 2. So what's a sub n minus 1 mean? The term before. Okay? So if you want to find, let's say, a sub 5, you need to use a sub 4. Okay? You see that? That's kind of cool. So take a look what we're going to do here. We want to find the 4th term of this recursive sequence. A1 is 3. Okay, that one you're given. That's your starting point. AN, now this is what we're going to use. So the next term is 3an minus 1 minus n plus 2. Okay, what? Okay, so let's see. So we have a1 there. Okay, a1 is 3. The next one I want to find is a sub 2. So n is 2 now. So a sub 2 is going to be 3 times, what's an minus 1? a1 minus 2 plus 2, so that's 9. Okay? All right. Because A1 is 3. Oh, right. So A sub 3 is 3 times A2 minus n, which is 3, plus 2. So how much would that be? 26. Okay? And now we need a sub 4. A sub 4 is 3 times the previous number, 26, minus 4 plus 2, 76. Okay, so do you see how you couldn't have found A4 before you found the other ones?
Yeah. How did you get 26?
So it would have been 3 times A3, right? Because it's A sub n minus 1.
No, for the one above. Like
Okay, so 3 times A sub 2, so that's 3 times 9, because it's the term before.
So you multiply.
Yeah,
2.
27
Oh.
minus 3 is 24, plus 2 is 26. Okay, what else? Okay, so the biggest difference is, with these, right, if I'm given an explicit formula like this, I can jump straight to like the 57th term and I can find it. But with this, I can't do that. If I want to find the 57th term, then I need the 56th, right? And for that, I need the 55th. You know what I mean? So you can only go step by step. You can't jump into like the middle of the list. Okay. Now, take a look here. The Fibonacci sequence. Have you guys heard of the Fibonacci numbers?
Yeah.
What about them? What have you heard about them?
You add them, you add like 4, and then it's like the spiral thing.
Right.
Yeah, and it's like in nature.
Yeah.
Like the golden ratio.
That's the yep. So you know quite a bit. Okay, so let's do this. Let's find them and then we can talk more about it. Okay, so look at what you're given. A1 is 0, A2 is 1. Okay? Now, AN is AN minus 1 plus AN minus 2. So what does that mean? To find each term, you have to add the one that comes right before it and the one that comes right before that. So you have to add the 2 previous ones. So for example, for A3, I have to add A sub 2 plus A sub 0. So that's 1. And what's A4? What do you guys think A4 is? 2. So if you list them, it's 0, 1, 1, 2, and then what would be the next one? 3, and what would be the next one? 5, 8, 11, 13, and so on. Okay? All right. So if you start with a rectangle down here in the middle, you see that white one down in the middle here? Right? Look at this. It's 1, 1, right? And the next one is also 1, 1. The next one that follows after that is a 2 by 2, right? So 1, 1, 2. And then each side of the next one is 3. So again, 1, 1, 2, 3. Then it goes to 5. Oh, I don't want this add. Right? So 1, 1, 2, 3, 5, 8, 13, 21. Do you see that? And you can like spiral out that way. So if you look at each of your fingers, the ratio is like this is like to the first joint here is it's like 2 parts, right? It's like 2 to 5 to 8 to what's the next one? 11, right? So like even that works in that way. So it's everywhere in nature. And then if you look at, let's say, like seeds in a sunflower seed, right? The first level has like 3, then it has 5, then it has 8, then it has, all sorts of things. And then
isn't it like if we take away like the 2020, the 21 by 21 cube, it's the same ratio, and it's just the 13.
Yeah. Okay. So do you see this one? Right? Like it's the same sort of, as you expand, the numbers expand in the same way. All right? So you can see it like all over in nature. Huh? So like in the first, right, so let's talk about convergent and divergent sequences. If you take the values in your sequence like this, and you graph them. So for example, the x-axis will be the ends, 1, 2, 3, 4. And the y-axis will be the values, 3, 9, 26, 76. Okay? If you graph a sequence like that, if you see that the values in your sequence, like this one started way up here and then it keeps going down. Do you see how the values in the sequence, little by little, are approaching a value of 0, right? If the values in the sequence are approaching a certain finite number, then we say that that sequence will converge, right? If the terms approach a unique number. However, take a look at this next one. The first term is here, y equals this one, then this, then this, then this, then this. But so do you see, like the further down you go, there does not seem to be a trend for all of those values to approach a specific number? We say that in that case, a sequence diverges. So this one converges, it's convergent, and the other one is divergent. Okay? Now, let's see if each of these examples converges or diverges. So here we have a sub n. This is the formula to find each of the terms. We want to find a sub 1, a sub 2, a sub 3, and so on. Graph them and see if they're going to converge. So take a look here for a minute. A sub 1, it's going to be negative 4,000 times negative 1 over 4 to the power of 1. That's 1,000. Okay? A sub 2 is negative 4,000, negative 1 over 4 squared. That's negative 250.
Why is it squared and not? Oh, no.
And then a sub 3 in the same way is 62.5. A sub 4, negative 15. The fifth one is 3.9. And let's just do one more. Sixth one is negative 0.97. Okay. What do you notice between each of these values? Is there a pattern? Yeah.
Whenever like n is an odd number, it's positive, and whenever it's an even number, it's negative.
Absolutely. Do you see how the sign alternates? You have positive, negative, positive, negative. That happens when you have something to the power of n, when you have a negative term to the power of n. Because if you have a negative term to the power of an exponent, if n is odd, 1, 3, 5, that's going to be negative, right? But if n is even, 2, 4, 6, that's going to be positive. So if you have a negative to the power of n, the sign will alternate. Okay, so that's like an aside. Okay, let's graph these things and see where they're going to go. Okay, when n is 1, that's the horizontal axis. When n is 1, an is 1,000. So horizontal axis is 1, vertical 1,000. 2, negative 250. 3, 62.5. 4, negative 15. 5, 3.9, and then negative 97.97. So yes, they're alternating up, down, up, down, up, down. But do you see a trend that the values are approaching a certain number as, as the ends increase? What number do you feel like they're going to approach? 0. And because of that, we say that this one is convergent, or it converges.
But it doesn't have to be 0, it has to be like 1.
Correct. It has to be a specific number.
Bless you.
Okay, so the next one. Is the sign going to alternate for this one, do you think?
Yeah.
Yeah, because you have a negative number to the power of n. Okay? So, a sub 1 is negative 2 to the 1 over 2, negative 1. Okay, who can tell me what a sub 2 is? 2. Then it's negative 4. Then it's 8. A sub 5 is negative 16. Sixth one, 32. Seventh one, negative 64. Eighth one, 128.
How far do you want to go?
Usually 4 or 5 is good enough, but I'm really like trying to make it like super obvious.
Got it.
So the first one is negative 1, and look at my scale, right? I did this so like each one is at a different scale so we can graph it better. So a sub 1 is negative 1, so it's way down here. Okay. And then a sub 2 is 2. 3 is negative 4. Okay, so we don't have to be NASA precise here. No one's going to go to the moon with these graphs, right? Like, we're not going to send anyone to the moon with these. We want the general trend, okay? So don't go, take out your calipers and make sure that, like it's, okay? So we're eyeballing a little bit. So a sub 4 is 8, negative 16, 32, negative 64, and then 128. So what do you think? Do the numbers look like 128 is over there. Do the values look like they are approaching a specific value?
No.
No. This is divergent. Yeah.
The previous graph, I missed if you said it.
Huh?
So the previous graph is okay.
Yeah. 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 Okay, next one. Do you think the next one is going to alternate signs?
Yeah.
No.
But there isn't. Oh, it's not negative in the thing.
So no. Good. Okay, so a sub 1 is 0.1 times 1 over 1, so that's 0.1. A sub 2, 0.0067. A sub 3, 0.406. A sub 4, 4 zeros again, and 57. So look at what I did with the grid here. I mean with the scale here, right? I'm going to 0.1 and negative 0.1, right? Just so, right, we can have like space here. So we start at 0.1, then we go to 0.0067 here. Oh, wait, 0.0067. I don't know if there was an extra number of zeros there. And then it's all the way down here and down here. So what do you think is happening to this one? Convergent or divergent? Convergent.
Wait, doesn't zeros make sense here, like the unit? Because when it
Zero is zero.
Yeah, I don't know if this one, I don't know if it could,
we get the idea.
you get the idea. So, yeah. Okay? All right. Okay. And do you have to graph this one to, like, do you really have to graph them to see them? Not really, right? Like, you can figure it out. Okay. So that was sequences. Now, what about series? If I took a sequence, which is just a list of numbers, and added all of those numbers up, it would be a series. So if I replace the commas with plus signs, it would be a series. So the series, a series rather, is the indicated sum of all the terms of a sequence. Now, what does indicated sum mean? Sometimes you have to add all of the numbers in the sequence. Sometimes it'll just tell you to add like the first 20 or the first 100. Have you ever seen like those mind puzzles? Like, what's the sum of the first 100 positive integers? Right? No? Never? No? Was it like a more of a 90s thing? No? No more? No one's doing TikToks on the first,
No.
So, a finite series is the sum of a finite sequence, and an infinite series is the sum of an infinite sequence. All right? So take a look here. This one is a finite sequence, right? And then this is the finite series that corresponds to that. All right? This is an infinite sequence because it goes on forever. This is the infinite series that corresponds to that one. Do you see how like you just keep adding numbers after one another, right? Okay. So the nth partial sum is the sum of the first n terms of a series. That should be of. Okay, and it's given the symbol S sub n. Okay, so to find the nth partial sum, you find all the terms and you add them up. So let's take a look at this one. We want to find the fifth partial sum. That's S sub 5. So the first 5. All right, so let's find the terms here. What's A1? Yes. Sum. Yeah. So A1 is -2. What's A2? 1. A3? Right? A4, 13, and then A5 is 22. So S sub 5, you just add all of them up. And you get 40. Okay? So here we want S sub 4. So that's A1 plus A2, A3 plus A4. Okay. So A1 is 3. Then 3 over 2. Then 3 over 4. Then 3 over 8. 45 over 8, which is 5.625. Okay, and it's equally acceptable to leave it as a fraction or a decimal. All right, last little bit. This first lesson is all about like getting to know the lay of the land, you know? Okay, let's talk about sigma notation. All right. You know how in English you have this letter S makes the S sound, and this is the lowercase s makes the S sound? Yes. And what's the letter in the Hebrew alphabet that makes the
Samech.
Samech?
Or Sin.
Or Sim. The same in Arabic. It's so interesting. Well, the sounds are the same. No vowels there either. Yeah. Very interesting.
They're really, because I think they come from like the late.
Okay, so in Greek, the letter that makes the S sound, the capital is sigma like this, so it's sigma. This is capital sigma, and lowercase sigma is this. Okay, and just like S is used for sum, so is sigma, right? It's used for sum.
What's the lowercase? How do you draw that?
So you kind of do like this thing and then a thing.
Oh.
That sounded just like Scotty.
I can't. You start from this. You start from this part, right? And then you just you wouldn't have to draw it.
It's like an A.
But like, yeah. So yeah, but like you start from here and you come down and you know, yeah, yeah. Okay, that's a sigma. Okay, lowercase sigma. It doesn't look as cute, that big. Okay, all right. So when you say sigma, right, A sub n from 1 to k, that means add up all of those terms from the first one to the kth one. Okay, so for example, if I have sigma n equals 1 to 4, n plus 1, right? I first put in n equals 1, I get 2. Then I put in n equals 2, I get 3. Then I put in, oh, these are all supposed to be pluses. Then I put in n equals 3, and then I put in n equals 4, and I add them all up. Okay? So basically you start from when n equals 1, and you keep increasing n until you reach 4. All right? And then from 1 to 4, 1, 2, 3, 4 is 4 terms. 1, 2, 3, 4, 4 terms. So that's what sigma is. All right, so let's find each sum here. We're going to find the sum of from 1 to 4 of n squared minus n. So basically what I want is a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. Okay, a sub 1, n is 1. And when I put n into that formula, I get 0. Okay, plus a sub 2 is 2 squared minus 2. A sub 3 is 3 squared minus 3. A sub 4, 4 squared minus 4. Do you have to write it out like that every time? No, I'm just doing it to illustrate, right? So this is just 0 plus 2 plus 6 plus 12, 20. Yep, good.
So does the actual stuff on top and underneath the sigma, like, not really, you don't do anything with that?
No, you just know where to start and where to end. You know to start at n equals 1 and to stop when you reach n equals 4.
Okay.
Yeah? Okay. So this next one, ooh, we're going to sum up all of these from n equals 1 to infinity. It's going to take a long time. So, okay, let's get to it now. Yeah, so, okay. So, what's the first one when n is 1? 3 over 10. 3 over 10. Because there's a 3 outside. 3 times 1, 10. Right. Plus, what about when n is 2? 3 over 10 to the 2. Plus 3 over 10 to the 3. Plus 3 over 10 to the 4. Okay, so that's not getting us anywhere. Let's just put plus dot dot dot. Let's see what we can do with this, right? So this is 3 over 10 plus 3 over 100 plus 3 over 1,000 plus 3 over 10,000. Okay, that's not any easier. Okay, so you know what? Let's just go to decimal, see if that's any easier. So 3 over 10 is 0.3. What's 3 over 100? 0.03. So the number of zeros is how many decimal places there are, right?
Yeah.
So 0.003, huh? Oh, yes. So,
She wanted to get.
no.
You spoiled it.
You're stealing my thunder. But yes, it is. I always want for someone to say that, like, immediately. Yes. Okay, so good. So look, if you just take these two, it's 0.3 plus 0.03, that's 0.33, right? If you align them, and then it's 0.333, and then it's 0.33333. So what this is 0.3333. Now, be careful. What is it that's repeating? It's just the 3 that's repeating. So technically, you're only allowed to put the bar on one of the 3s, not all of them. Because it's not like it's 3,333 that's repeating. It's just a 3 that's repeating.
So you couldn't just write 0.3 with the thing.
You can. If you see it from the beginning, you can do that as well. You can do 0.3 with the bar. And now, how much is that as a fraction? 1/3. Isn't that cool? If you sum up an infinite number of these, you will just get 1/3. Right? Isn't that cool? Yeah, okay. All right, so let's do this other one. Ooh. Next. It tells us to write the series in sigma notation with the lower bound given. So basically, we are given this, and we need to find this. Okay, so we're going backwards. And when it says the lower bound is given, that's this at the bottom. Okay, so the way this is going to look is sigma n equals 1. Now we just have to figure out what goes here and what goes here. That should be easy, right? Well, let's see. So here's what you're going to do. If the lower bound is n equals 1, let's put down all of the n values here. 1, 2, so that's n equals 1, 2, 3, 4, 5, 6, 7, 8. Now what you want to do is you want to find a relationship between, whoops, n and the value. So for example, what can you do to this number to get that number? What can you do to the red number to get the number above? What can you do to this one to get that one above? What do you all think? What's the relationship? How do you go from 1 to negative 2?
So how do you know that the negative two starts out
Minus
with
2?
three? How do you know that like a negative
Because
two-
that's the lower bound. n equals 1 is the
So-
lower bound.
the first one in that like series always has to be n equals 1.
Right, or if it was n equals 4, then it would be 4.
Okay.
Yeah.
But then why did you like instead of writing like -2, -1, you wrote like to up to 8? Why did you do that? Just because there's 8 different values?
Yes, because there are 8 different values. It says, this tells you to call the first one number 1.
Even though that's not the case.
Right, because well, it's the first number in the list. That's what that says. So this says this is the first number in your list. So that's the second number and the third number and the
Got
fourth
it.
and the fifth
Yeah.
and the. So now you need to figure out a way to go from this red number to there. You subtract not 2, how many?
3.
3, and from here to here, does that work?
Yeah.
And does it work for all of them if you
Yeah.
subtract 3? So then these red numbers were n, right? So this would be n minus 3. And how many total, like what's the last n over there? 8. So that goes there.
What is it? The power of n?